Hey everybody, polynomial and rational functions. Chapter 3 is certainly packed full of stuff. So a lot of the things that we're going through in this chapter are going to be similar to like the binomial square and some of the other items where I said it's so much better if you know it than to try to wait and calculate things. So there's going to be a whole lot of things that you need to study. You're going to use that S word and study it, or print it out and put it on your wall. Take a look at it for 10 minutes a day. And 10 minutes a day, if you did that consecutively, actually works, but you have to do it consecutively. So here we go. We're going to look at polynomial functions and their graphs. Look at some basic polynomial functions, the end behavior and the leading terms, using zeros to graph the polynomials, the shape near a zero, and local maximum and minimas of a polynomial. So again, we're using the same format for polynomial. We're just saying this will work for all the polynomial that is in this form right here. So numbers A0, A1, A2 are going to be the coefficients that are in the front. The constant term is going to be what's out here on the end without an x. Actually, maybe an x to 0 power because it's 1. But anyway, you don't see an x here, so that's a constant term. And the leading coefficient would be the coefficient that is with the exponent to the highest degree. Lots of stuff here again. So this is the leading coefficient. So this is something that would be good to put on a 3x5 card. This is the leading coefficient. The degree of the polynomial is the highest exponent, which is 5 here. The leading term would be this entire term, 3x to the 5th. And here it shows you the other coefficients, which coefficient again would be 3, 6, -2, 1, 7, and -6. And finally, that constant term is the one that you don't see in x, and that would be -6. So some examples of polynomials are just if you have a constant, it's a degree of 0 because you could actually justify putting an x to the 0 power here because x to the 0 power is 1. So you could say it's there and that would give it a degree of 0. And we have a degree of 1 here because our linear function, we have 1 as our highest exponent, degree of 2, and degree of 3. If it's just a single term, it's called a monomial. It's still a polynomial, but it's a polynomial that is a monomial. So x to the 3rd or -6x to the 5th would be monomials. Polynomials that are monomials. Going to look at graphing some basic polynomial functions. If it's a polynomial, one of the things that you could say about it is that it is a continuous function. So just like before when we said the domain, the range in the domain, not necessarily the range, the domain is all real numbers. Well, because a polynomial function, the domain is all real numbers, you're saying that all real numbers work when you input them into the polynomial. That also means if they all work, there are no breaks. So as I travel along this polynomial function, there are no breaks in the function, so that would make it continuous function. And the simple polynomials that we know are two of your parent functions, which is y equals x. We'll go right through the origin, and y equals x squared, which is our parabola parent function here. Other parent functions that we've looked at are y equals x x cubed. When we get y equals x to the fourth, it's still a polynomial, but notice right through here it gets flatter, and it will get even more flat if you have x to the sixth or x to the eighth. And the same if I have y equals x to the fifth with the cubic function, this area is now going to be more flat and then have a steeper turn here, steeper slope on the ends. However, as the degree n becomes larger, the graphs become flatter around the origin and steeper elsewhere, as I just said. So sketch the graph. So right here we see in the front that we have a negative, so that should tell you that this flips around the x-axis. So here was my x to the third, and I just flip it around the x-axis. So I just take this and flip it over, and now it becomes the red line here. Let's look at B. B looks like the front is going to be positive, so that should be a flatter parabola, and it's -2, so it looks like I'm going to shift it to the right 2. Okay, there it is. It's a flatter parabola. Right here you can see it's flatter than our normal parabola. You can plug in a couple points to get an idea around here of how flat it would be. And also it has shifted, like we said, to the right too. Okay, so now we want to take a look at, this is -2x to the fifth plus 4. So my y equals x to the fifth would be right here, this function that, well, actually this would be the negative of that function. If we flip it around the x-axis, so before it was, let me use a different color. Let's use blue. Guess it is blue. Let's use purple. I really don't use purple much. Okay, so this actually comes up here. And, you know, again, my art is not the best. Like that. Okay, so that would be my y equals x to the fifth that's shown right here. And then I know that it is -2 x to the fifth, so I flip it around the x-axis. The 2 is what gives it its steepness here. Again, plugging in a couple points will help. And then finally, I see this +4 on the end, and that means I'm going to take the entire thing that I flipped around the x-axis, and I'm going to lift it up 4. Now we're going to look at the end behavior of leading terms. And the reason these help us is that if we're graphing these functions and we know the end behavior, then we know whether or not our answer is correct and our graph is correct. If we're using a graphing calculator, then we'll know whether or not we plugged it in the graphing calculator correct. I often see people just plugging stuff in the calculator and putting it on tests, and then they really don't understand what they've put in, so it's not put in correctly, and then the calculator really does you no good. So it's better to understand what it should look like so you can check yourself with a calculator instead of relying on the calculator to be your brain. Okay, if I have this symbol here, this means x approaches infinity. Okay, x becomes large in a positive direction. As x approaches infinity, becomes large in a positive direction. And then this would be x approaches negative infinity, also meaning x becomes large in the negative direction. All right, these are the 4 possible types of end behavior. So here is the first one. This would say as x approaches infinity, which means as x would get larger this way, then y approaches infinity. Y would get larger this way. Over here, as x approaches negative infinity, which means x will go this way, then y also approaches negative infinity. Y will get smaller this way. Here I have as x approaches positive infinity, which means as it gets larger this way, my y gets smaller and smaller, so it approaches negative infinity. And then the opposite of that would be x approaching negative infinity as y gets bigger and bigger and approaches positive infinity. Now notice these two have odd degrees, and when they have odd degrees, we have it starting on one end and then coming up through the other end. So it's not symmetric. It might be symmetric about the origin or about a specific place, possibly, but it's not going to give us this look here where we have our end behaviors being the same. So our end behaviors are going to be different when it has an odd degree. Now when p has an even degree, remember degree is the highest exponent in a polynomial, we're going to see that the end behaviors are then the same. So for instance, if I have x approaching positive infinity, I have y approaching positive infinity. And if I have x approaching negative infinity, then I have y approaching positive infinity. So my end behaviors for my y values are the same. They're both going up regardless of whether or not I am going to the left or to the right, positive infinity to negative. Now, that's when my leading coefficient is positive. We already knew that because we know when we have a parabola that it'll go concave up. Okay. Now, if the leading coefficient is negative, I'm going to be concave down on the most part, right? Except for these two little areas, but right here on the ends, I'm going to be concave down. And then I also have as x approaches positive infinity, then y approaches negative infinity. And as x approaches negative infinity, y still approaches negative infinity. And that's if my leading coefficient is negative. Okay, so there is so much information in this one little chart. You know, again, I didn't really emphasize, but over here, again, you'll have this type where I have my y and x both being negative, approaching negative when I have a leading coefficient that is positive, and then my y and x are both approaching positive in that case. Now, one good way to remember this, that positive is a negative and a negative, or positive and a positive will give you negative, or will give you positive, sorry. So I like to find ways to try to remember things like this, so that's one way you can remember. And similarly, if I have a positive and a negative, then that will give me negative. So if my coefficient, my leading coefficient is negative, then my x and y approaches are going to be the opposite directions. Okay? So lots of information here. And what do I want you to do with that information? You need to know it. Determine the end behavior of the polynomial. Let's look right away. I see here's a negative in front of the leading coefficient. The leading coefficient is negative 2x to the fourth. I know that it's even, so my end behaviors are either going to be going up or going down, and I just need to know when it's negative, does it go up or does it go down? Do my y values on my end behaviors go up or do they go down? And hopefully you are thinking that they go down. So polynomial has a degree of 4. The degree is the highest exponent. The leading coefficient of negative 2. So it has an even degree and a negative leading coefficient. So as it approaches negative infinity, x is going to, or actually I should say start with the x, it makes more sense. As we travel to positive infinity, my y values are going to be going to the negative infinity. And as I travel on my x to negative infinity, my y values will also be going to negative infinity. So, I should have already known from previous chapters that this is going to be something like this on this end and this on this end, and who knows what it does like in here, who knows, okay? But on my ends, it's going to look like this, going down. Excuse me. And there it is. Okay, so as you can see, we have our, as x goes to positive infinity, my y value goes to negative infinity. And as x goes to negative infinity, y does in fact also go to negative infinity. Using zeros to graph polynomial. What does that mean, using zeros? That simply means that you are solving the equation. Okay, when you solve an equation and you have factored it, we set it equal to 0. That's why it says using zeros. Because when you in fact set something equal to 0, you're saying, where will it be 0? So that's why we call it using zeros. Okay, and some clarification of what it means. If I plug a c value and I'm calling it a 0 of p, that means when I plug the c value into the polynomial that I'll get the value of 0. So the other things that I can say about that, not only is it a 0 of p, but that also means that x equals c is a solution of the equation. And it also means if I would subtract c from both sides, x minus c is a factor of the polynomial. And the last thing, well, maybe not last, but another thing that it means is that c is an x-intercept of the graph of p. So it does, in fact, touch the x-axis at that value. Finding the zeros of a polynomial, we will factor it and use the product property. For example, if we find the zeros of a quadratic, that's great because we already know how to factor a quadratic equation if it does in fact factor. And this one does. It will give me x minus 2 and x plus 3. So that tells me that if I plug 2 in here, I will get 0. If I plug negative 3 in here, I will also get 0. So that tells me that 2 is a 0 of the polynomial. That tells me that x equals 2 is a solution of that equation. It tells me that x minus 2 is a factor of this polynomial. And it also tells me that 2 is an x-intercept of the graph of p. Now I could go back and take all of these same things that I just said about 2, and I could say that's also the case for negative 3. Negative 3 is a 0. x equals -3 is a solution. X minus -3, which is x plus 3, right? Minus a negative would be plus, is a factor. And -3 on the axis is an x-intercept. So it does hit -3 on the x-axis. So the following theorem has many important consequences. We use it to help us graph polynomial functions. This is the intermediate value theorem. Now this should be called common sense theorem. If P is a polynomial and you have 2 points, point A and point B, when you plug them in, you get opposite signs. One of them is negative, one of them is positive. Then that tells you that somewhere along the line, it crosses 0 on the x-axis. So in other words, all I am saying is if I have an axis, coordinate plane, and I take some kind of graph and I'm going like this, well, my values up here for my y are going to be positive. My values down here for my y are going to be negative. So that tells me that it has to cross the x-axis somewhere. That is all this intermediate value theorem means for polynomials. So here again, an example. Here I have negative values. Here I have positive values. So it has to cross the x-axis and give me a 0 value somewhere. So some guidelines for graphing polynomial functions. The factors of the polynomial we'll call real zeros are the x-intercepts. We're going to make some test points, include the test points to determine whether the polynomial lies above or below the x-axis on the intervals determined by the zeros, including the y-intercept in the table. So we're always going to want to check that where is x equal to 0 so we can find the y-intercept. We'll look at the end behavior of the polynomials based on the information that we looked at a couple slides ago for odd exponents, even exponents, and whether or not the leading coefficient is positive or negative. And then when we graph, we'll plot the intercepts and the other points we found in a table and sketch a curve that hopefully is close to exhibiting the behaviors. So here's an example. We want to find the zeros of P and sketch the graph. So before I even start doing anything, I want to take a look. I see that my leading term is x cubed. So that tells me that it's going to somehow represent something that looks like this, because I'm going to have end behaviors that are different. And then I want to find the zeros. Now, this is a nice one because I can see that I can factor an x out of each term here. So I'm going to do that first, and that will give me a quadratic. And then I can factor my quadratic if it factors. So you can see here that now I have zeros that are 0, 3, and 1. If I put any of these in down here, I will get 0. So those will be my zeros. 0, 3. Oh, wait. Okay, so this means signs are different. And so I'm going to have this as plus. I tried to check all the mistakes on this before I went through it today, but this needs to be a positive right here. So my 1 is in fact right here negative. So here we go. -3 plus 1 is -2. Signs are different. One's positive, one's negative. Okay. Now that we know that the x-intercepts are 0, 3, and -1, we know that the y-intercept is 0, 0, 0. We can make a table of values and test some points in between to see what it looks like. I know it's odd degree and the leading coefficient is positive, so it has the following behaviors as we looked at before. Now you may not remember these right away, but again, this is something that you're going to need to know. Here we are, we have our end behaviors as x equals, or as x approaches -infinity, y approaches -infinity, as x approaches positive infinity, y approaches positive infinity. Plug in some values so I can see the behavior around here. I know that it hits the graph at -1, also at 0, and at 3. So now I can give myself some points in between here and between here. When I say that, I mean between the -infinity and the first x-intercept. I'm going to put a few points in here so I can look at this behavior between these two, and then also between these two, and then an end behavior up here, just to give me a directional point. All right, shape of a graph near a 0. In general, C is a 0 if the corresponding factor -C occurs exactly m times in the factorization. Then we say that 0 of multiplicity m. I will explain what that looks like in a minute. By considering test points on either side of the x-intercept C, we conclude that the graph either crosses the x-axis or doesn't cross. Moreover, it can be shown by using calculus, which you'll do hopefully the next time you take a math class. Okay, so if m is odd, the multiplicity of C, so if m is odd and m is bigger than 1, it's either going to look like this or it's going to look like this. If m is even and it's greater than 1, then it's going to touch here and it's going to stay on the same side, or touch here and stay on the same side. So let's take a look. Here we have a polynomial. This looks like if I multiplied all those together, I would have an x to the 4th, I would have an x to the 3rd, and I would have an x to the 2nd. So since it's all factored, I'm going to have a multiplicity of 4 for my 0 value, because if I set that equal to 0, I would really say that the answer is 0 4 times. Now, we don't really say the answer is 0 4 times, because if the answer is 0, we just need to know that once. However, it'll help us with the shape of the graph to know that it has a multiplicity of 4. Now, also 2, if I put 2 in here, I will get a 0, and it has a multiplicity of 3. And here I'm going to put a -1 in, and it has a multiplicity of 2. So the 0, 2 has an odd multiplicity, so it will cross the graph at the x-axis, and the x-intercept is 2. So again, important stuff, whole bunch of stuff. So that means it crosses the graph at the x-axis and has an x-intercept at 2. What about the other ones that have the even? Well, 0 and 1 have even multiplicity, so the graph doesn't cross the x-axis at those 2 points, but it does in fact touch it, but it just doesn't cross. Now, since it is a polynomial of degree 9, how did I get that? I need to add all of those exponents together because when I multiplied them, that's what would happen. So I have an x to the 4th plus x to the 3rd plus x to the 2nd. That gives me x to the 9th. So it's a 9th degree. It's an odd degree. So it's an odd degree, has a positive leading coefficient. So that means as it approaches, x approaches positive infinity, y will in fact approach positive infinity. As x approaches negative infinity, y will approach negative infinity. So here's this crazy graph. We're definitely going to have to put in some points. So we want to place our x-intercepts here first. Okay, so now I have those values here, and hopefully you took a minute to see that these are even multiplicities, so that means they don't cross the x-axis. It stays on the same side. So you have little, kind of like little baby parabolas right here, and right here, okay? Now up here, this has the odd multiplicity. This is the one where we have the 3rd. So we have an odd multiplicity, so it does in fact cross the x-axis. All of this information is important for you to know. Now we're going to take a look at local maximum and minimas of polynomials. We already looked at local max and minima when we were in chapter 1 as a review. So a local maximum point would be the highest point around a certain area. So this would be a local max. This would be a local minimum. And we'll say that, this point again, this is just emphasizing once again that it will have a local max and a local minimum point. The local max and minimum points on the graph of the function are called the local extrema. Why not give it another name, right? So local max and local minimum points are called local extremas. A polynomial of degree n may in fact have less than n minus 1 local extremas. For instance, if I have an x to the 5th power has no local extremas even though it is of degree 5. So the preceding principle tells us only that a polynomial of degree n can have no more than n minus 1 local extremas. Again, what does that mean? And I still check for these now. That means if I have a degree of 5, it can only have 4 places where it would have local max or minimum points. Can't have any more than 4. Why? Because that's n minus 1. N is 5. Okay, so how many local extremas do they have? This one is an x to the 4th, so it would simply have 3. This one is an x to the 5th, so it would have 4. This one is x to the 4th because it would have 3. No more than. I shouldn't say have 3. No more than 3, no more than 4, no more than 3. It could have 1, 2, or 3. It could have 0, well, 0, not 0, 1, 2, or 3. Okay, so here is an example of that. We have the x to the 4th equation we looked at. Notice I have a local minimum, a local maximum, and a local minimum. I have 3. Here I have an x to the 5th. Here I have a little local max. Here I have a little local min. Here I have another little local max. And here I have a local min. 4. Now that doesn't always mean they're exactly going to have that. Like I said in the last slide, it's no more than that. So there might be something that causes them to have less. For example, here I have an x to the 4th power, but I only have 1 local minimum. So that's why it could only possibly have up to 3 local extremins, but it only has 1, and that is a local minimum. And that's because of all this stuff after that causing changes.